Hey everybody, I'm Amelia Thompson, your host for today's Würth Elektronik webinar, partnered with DigiKey Electronics. It's going to be a scorcher out there. I think it's a day high of 95 or 35 for, the rest of the world. It's going to be really warm. Hope everybody is staying inside, staying safe, staying cool and hydrated. Today's webinar is how to interpret the datasheet values and specifications of capacitors, partnered with DigiKey Electronics. And our presenter today is Jon Izkue Rodriguez, hardware engineer in our capacitor and our resistor division here at Würth Elektronik. Now, a few housekeeping rules. If you have any questions during today's webinar, I ask that you ask them in the questions box. You can find the little question mark there. Go ahead, ask your questions. You can test it out right now if you want. Do you prefer winter? Do you prefer summer? Hot versus cold? I'm a little curious because here in the United States, we love our air conditioning. Not really the case with the rest of the world. So just wondering about that. Now, along with your questions, if they don't get answered during today's presentation, don't worry about it. We will gladly answer them after the presentation. We have your email address and we will be answering your questions then. Along with your email address, be sure that you also look for the video on demand that'll be headed your way in the next week or two, as well as a PDF of the slides. You can always find them at www.we-online.com/webinars. Fall is the best, somewhere in between winter and summer. I have to agree with you there. That's a very good answer. I would say spring here, but we usually get around 20 inches of snow in the spring. So not entirely sure that one is my favorite. Because you registered for today's webinar, you will automatically receive the slides and the video on demand. Again, just look for them in your email. Don't miss our next webinar. It's coming up on August 16th. It's Transformers. What characteristics are important to you? Of course, partnered with DigiKey Electronics, the exclusive sponsor of our Würth Elektronik webinars. Register online at www.we-online.com/webinars. Now let's begin today's Würth Elektronik webinar with Jon Izkue Rodriguez. It's how to interpret the datasheet values and specifications of capacitors, partnered with DigiKey Electronics.
So yeah, thanks Amelia. Good morning and good afternoon, I guess, for the rest. My name is Jon Izkue Rodriguez. I have been working at the company for 4 years at the capacitor division, capacitor and resistor division now, and I take care of some hardware projects and demonstration circuits regarding capacitors. Mostly, I do some technical support and technical marketing, and also, as you will see, lots of measurements of capacitors. And also, I take care of the measurements in RedExpert. So let's start. One moment. Yeah. So the topic of this presentation is very broad. So it's more like tips and a little bit of this and a little bit of that. We could be talking about datasheets for hours, but we don't have that much time, and yeah, datasheets are not that interesting. So I will be talking about some specific things that are included in the datasheets and some very important things that are not included in the datasheets. First, one moment. First, we will be talking about MLCCs, our very beloved components, also a little bit misunderstood components. I will show you some data sheets, and we will discuss some properties that are in the data sheet. Then we will see some properties of aluminum electrolytic capacitors. And finally, in the end, I will show you how you can find some extra component information in our online tool, RedExpert. So to start, let's look at one very popular capacitor. This is the class 2 X7R MLCC, 10 microfarad, rated voltage 50 volt. So this is the box that most of you will be looking at. So all the 10 microfarad, all packed inside of a size form of 1210. So this is only 3.2 millimeters long, 2.5 millimeter wide, and 2.5 millimeter high. So yeah, it is an engineering and scientific wonder to get so much capacitance inside of a small package. But now, of course, everything comes at a price, and some of you might guess that the rated capacitance may not be that good. There are voltage, frequency, and temperature dependencies. So starting from the basics, capacitance is the defining characteristic of a capacitor, obviously. So to keep this short, we can say that capacitance is a measure of the electric charge that the component is able to store for each unit of electrical potential. So C is equal to charge Q divided by voltage, as you can see in this formula. So the capacitance of an ideal capacitor is a constant, but as such, we can see it in this formula. But sadly, we cannot assume that the capacitance will remain constant in our operating conditions. So before we start with DC voltage, let's look at the conditions of the measurement. So we can see that this capacitor is measured with a signal of 1 volt RMS, with a frequency of 1 kilohertz and everything in a room with temperature of 25 degrees Celsius. But the voltage, which we can set up in the measurement equipment, is also important. So here I plot the capacitance measurement versus the test signal at the capacitor. As you can see, the value is fine at 1 volt, but RMS. But if I had only set 1 millivolt RMS as it is very common as default setting in some equipment, I will be outside of the tolerance limits of the capacitance. So maybe I can imagine I will be calling my capacitor provider and complaining about quality issues. So I want to show you something else about this. In the right, you can see some examples of the measurements we offer in Red Expert. This is the same capacitance variation for different test signal. The LCR meters have some output impedance in the path of the test signal, which means that the capacitor will only see part of the test signal that we set, for example, 100 ohm. So some LCR meters have, for this reason, some LCR meters have some kind of level control functionality. For example, in the E4980A meter, LCR meter from Keysight that you can see in this picture, there is something called ALC, which means automatic level control. When it is enabled, the device will monitor the actual voltage at the DUT and increase the signal output when needed. Sometimes, even with the ALC, the measurement equipment will not be able to provide enough power to the DUT. This is not a problem, but the user has to be aware that if or when the test signal that we set is actually in the capacitor, because that's the point where it was specified. So in this graph, you can see different settings with LC on and off, 20 hertz and 1000 hertz. So all the measurements are different, especially when we change the test signal. So we cannot compare these measurements to each other. So we have to know in which settings exactly we are measuring capacitors. So let's talk about another big thing, dissipation factor. It's also called tangent delta or tangent delta. If we consider the complex impedance of the components, so the dissipation factor is the ratio between the real part and the imaginary part, as you can see in this diagram. In capacitors, it means the ratio between ESR and capacitive reactance, which is here, as you can see in the formula. So for this specific part, we have a maximum value of 10%. Again, this is defined with the same conditions as the capacitance, with 1 kilohertz and 1 volt signal. Sometimes dissipation factor is used to calculate an estimation of ESR, but here it is even more important that we take into account the test frequency. When you convert dissipation factor to ESR, you have to use the frequency at which it was defined. So 1 kilohertz in this case. So this is the calculation of ESR. It is easy to calculate the ESR at this point, but only at this point, because the dissipation factor cannot be assumed to stay constant in other frequencies. So let's look at the same issue in another way. I measured the impedance characteristic of the same ceramic capacitor. In the left, you can see the black line, which is the ASR as the real part of the complex impedance. In blue, you can see the imaginary part, which is called the reactance. Up to the self-resonance point of around 1 megahertz, the impedance of the capacitor is defined by the capacitive reactance. At higher frequencies, the parasitic inductance will increase the reactance and it will dominate the impedance. At this point, the capacitor will act like an inductor. So let's go back to the dissipation factor issue. Here's the formula again. So you can see in the plot that from 100 hertz to up to 10 kilohertz more or less, the relationship between reactance and resistance is more or less constant. So they are parallel lines. So now I plot the dissipation factor calculated with this same R and X measurement. So you can see that up to 10 kilohertz, the dissipation factor is quite stable. But the assumption that the dissipation factor will be constant at higher frequencies is very wrong. When you are looking at ESR and dissipation factor specifications, I encourage you that you go back to impedance notions and make some calculations and draw some graphs, even with ideal capacitor conditions. I hope that this is understood. If not, yeah, you type your questions anytime. So we are going to talk about another big topic, DC bias. I guess you were waiting for this. I hope you are aware of the capacitance drop that some MLCCs have under DC voltage. This is called the DC bias effect of ceramic capacitors, of course. It will not affect class 1 ceramics like MP0 but yeah, for ceramic capacitors of class 2, which have high capacitance, it might be a huge issue. And also it's not an issue for any other kind of capacitors. In this graph, I have plotted the capacitance versus DC voltage of 4 different MLCCs with 1 microfarad and 50 volt rating. So DC bias is mostly reduced selecting bigger size capacitor. So you can see the blue is the largest capacitor and it has the smallest dependency of voltage. But the smaller 0805 capacitor is it has a very reduced capacitance at rated voltage. So we don't provide this kind of curve in the datasheet. If you can remember, we specified 1 volt AC test signal and nothing else. That means 0 volt DC voltage. This extra information is provided in our online tool RedExpert, which I marked here. I will talk later about that. Most manufacturers give little or known DC bias information in the official datasheets like us, only in additional documentation or online resources like RedExpert. So, like other aspects, DC bias may not be so simple as showing a graph like this. So in the process of getting a DC bias curve, there might be some decisions taken which will affect the result. We were having some issues with our measurements because the results were not always completely repeatable. We noticed that there is a huge difference when you measure the capacitance, increasing the voltage from zero rated voltage and the reversed sweep, as you can see here. So, excuse me. When we start with full voltage here, and after waiting some seconds, we do the voltage steps down from rated to zero. So the reverse process is plotted in the black curve. The result is way more repeatable if we do it that way. There is a big difference in the behavior, as you can see at 10 and 15 volt steps. There are huge difference in the DC bias behavior. So this difference is similar as the hysteresis that we know from magnetic materials. We call this the polarization of the ceramic. And there is more to this. Manufacturers may be measuring DC bias with a different procedure, and they may or may not be transparent about what is the procedure that they are using. So, excuse me. So we were worried in this case about the 10 microfarad ceramic capacitor, which had a worse DC bias curve or a worse capacitance drop than some of our competitors, at least when we were looking at the data from their website. So we ordered some samples from different manufacturers and we measured them ourselves. And what we noticed was that the difference was quite small, but there was a big, a very severe case that you can see in this graph in red. This is the curve the competitors show in the website. And as you can see, when we measured it ourselves with the procedures I described before, the dotted line is the normal method and the black one is the reverse method. Yeah, we have a much more comparable result. So we have no idea how they measure it. So the results that we got are way more realistic, and we can compare them with our data. So in my suspicion, maybe the operator did not wait enough when they were measuring. For example, using the DC bias measurement fixture that you can see in this picture here, you have to take into account there is a 200 kilo ohm resistor in series with the voltage path. So you can calculate with easy RC calculations. We know it takes about 10 seconds to reach to charge the capacitor of 10 microfarad to any given voltage. So that means they should have waited at least 10 seconds in each voltage step, and probably they didn't. So they got much better results because the capacitor was not charged at the test voltage. So again, let's look at the same issue in a more detailed way. Also the polarization. So using a vector network analyzer, we measure the full frequency spectrum of the same component from 1 kilohertz up to 1 gigahertz. So as you can see, the impedance, the resistance, capacitance, series capacitance, and series inductance, quite normal measurement. So we have a nice measurement setup that you can see in this picture. With it, we can measure capacitors with the shunt-through method and also apply a DC voltage to the capacitor, and everything without damaging or killing the VNA. So we applied some DC voltage to see the effect in the whole frequency spectrum. So we made 10-volt steps, and we can see the effect in the measurement. The capacitance drop that we saw before can be seen clearly in the capacitance graph. The higher the voltage here, the lower the capacitance values, of course, as we saw before. Of course, this drop means we have an increased impedance. And also, the self-resonance here is shifted from around 1.2 megahertz up to 3 point something megahertz at 50 volt. So you can notice around 700 kilohertz, we can see also a smaller resonance or anti-resonance effect. This is caused by the piezoelectric effect affecting the ceramic material. You can also see it here messing with our ESR measurement. The electric field that appear between the electrodes when we have some DC voltage will mechanically stress the ceramic, and in some frequencies this piezo vibration will interfere with the test signal or with the vibration from the signal. So we don't have to go into detail, but it's interesting for you, I think, to know that it can happen. This is the reason in some combinations of frequency, voltage, and MLCCs or capacitance values, we can create the singing capacitor effect. If you have any issues or questions about this, don't bother. Don't hesitate to ask here or later with my email. So perhaps you noticed before that that the last step I measured was again a 0 volt measurement. So I plotted the 0 volt again measurement, which is after. This is what I want to show you. What happens when the ceramic capacitor was under DC voltage for a few minutes, and then after completely discharging it, the frequency spectrum will show a clear deviation from the first measurement. So I only have the two measurements to compare now. So you can see here a sustained capacitance drop, and also a clear deviation of ESR, which is also increased. And also we have some rest of the piezo effect. So so this is a permanent polarization of the ceramic. When we make a new MLCC measurement, we have to do a thermal treatment to refresh the capacitor and get again the 0 volt, the fresh measurement. So let's look back again at the datasheet, and here there is a permanent polarization of the ceramic. So we have this note about preheat treatment. The idea is to hold the component for some time, at half an hour at least, over the Curie temperature. And with that process, the component will be in a refresh condition regarding both DC bias and aging. The Curie temperature of this barium titanate ceramic material is about 120 or 130 degrees Celsius. Of course, this applies to ideal laboratory conditions. In this picture, you can see our very high-tech baking oven that we use for this procedure in our small lab. We also state specifically that the preheating here is only necessary for class 2 ceramics and not for class 1 ceramics. But we also have good news for our customers that are worried about this. You can get this refreshing effect in the reflow soldering process, even if it only takes some seconds. So let's talk about edging. It shouldn't be a big issue for ceramic capacitors, but it can happen. It depends on the ceramic material, and there are inside of the class 2 material range. You can see in this graph there are different aging effects. In this graph, you can see a number of all ceramic capacitors. which had some aging issue, and the effect of the reflow soldering in the capacitance measurements. And these were all samples, 40 samples, and they were measured once before reflow in the in the gray plot, and they were measured again after reflow soldering, and we got this much better result. So as you can see, the soldering was enough to reset the previous polarization and any aging effect. This significant improvement, this is better described in this graph, where the heating can reset any polarization or aging of the capacitor. You can have more information on this topic in the support note SN011 that my colleague Frank Puhane wrote. Now let's look at a different capacitor technology. So we have the datasheet of THT aluminum electrolytic capacitor of 2.2 microfarad and 450 volt rating. So it's a relatively small one. It's a picture of a different LCR meter from Rode, a new one, measuring NICAP, but not the same that we mentioned in the datasheet. And also, as a small joke, you can see we set everything wrong in this setup. So if you pay attention to the measurement conditions of capacitance, this time is 250 millivolt and only 120 hertz. So everything here is actually wrong, and we're not getting the result we expected. So again, it's easier it's very easy for you to make the mistake of not having the right settings in your SCR meter. So let's test that information. So I plotted here the series capacitance versus the frequency of that capacitor, which I measured with an impedance analyzer. So it starts at 2.2 microfarad, so it's absolutely correct measurement at 120 hertz, around here. But it drops very fast at higher frequencies. So the second arrow is at 100 kilohertz, and you can see we only measure a capacitance of 0.8 microfarad here. The last bump here that you can see around 45 megahertz is the self-resonance point, and the capacitance values after that are meaningless for our purpose. This behavior of gradual capacitance loss is characteristic of electrolytic capacitors. And yeah, if you're worried about using them at high frequencies, you should be able to measure this area or contact us for more information. So after we saw that graph, should we be worried if we are using the capacitor at about 100 kilohertz? Maybe not, or maybe. It depends. If you really need that capacitance in your application, then maybe you can have a problem. On the other hand, as you can see in this graph, the series resistance CSR is so large that it completely dominates the total impedance around that frequency. So at 100 kilohertz, it doesn't matter so much if we have more or less capacitance, because in the filtering aspect, it's a resistor in this point. So now we are going to talk about another aluminum electrolytic capacitor issue, and this is the leakage current. So interesting parameter, and also misunderstood. So it is defined as the current flowing across the insulation of the capacitor. But the definition of the measurement is that the current is the current measurement after setting the rated voltage for some specific time, for example, 5 minutes. The leakage current drops with time, as you can see. So this is the value that we take as leakage current for this case. But the left part of the diagram is the charging current. So it's difficult to discriminate at which point it becomes just the leakage current. So that's the reason sometimes it's defined by 1 minute, after 2 minutes, or even after 5 minutes. And let me tell you something about the other reading completely the data sheets. So I recommend sometimes to read the datasheets to the end. I guess nobody have time for this. This datasheet is 9 pages. Anyway, this is the section called cautions and warnings, and you can see. And you can see this is the page number 6 of this case of this ECAP datasheet. Under the section storage conditions here, we state some recommendations like no direct sunlight, room temperature, other stuff. But let me highlight these important points. So this part is the important one. The second part, the leakage current will return to normal level when applying the rated voltage before use. This information is not widely known by many developers because they don't care how long the parts might sit in their warehouse, or even less in our warehouse. So if the parts were stored, the capacitors were stored for a long time, some degradation will happen in the oxide layer, in the dielectric. So we describe here the reform process, which is a self-healing property of aluminum mid-caps. This reform process is similar to the process that we do during manufacturing to form the oxide layer. So after 30 minutes at rated voltage, the degraded oxide layer will form again and the leakage current should be fine. But again, should we be worried about this? We can measure this effect, as you can see in this diagram. So I took a very old capacitor and I measured the leakage current myself for 5 minutes, as described in the datasheet, with a series resistor. So I got the red curve here. The reforming process, as we define, is actually happening as we measure leakage current. So I only have to keep the voltage for 30 minutes, and then after discharge and waiting some minutes, I measure the leakage current again, and I plotted it in the gray curve, sorry. So you can see there is a big improvement, and this is all that happened after all the shelf time. So the capacitor was working perfectly. Only the leakage was a bit more. Still, the specification in the datasheet is still giving a maximum value many times higher. So the reason for this is that the maximum value will apply for the whole lifespan of the capacitor, and also this leakage current may increase at higher temperatures. So to take this into account, we specify a much higher leakage current, but you have to take into account that in the reality it will be much lower in the normal use. So before I finish, I want to talk you about Red Expert. Maybe you are already familiar with Red Expert. This is our online component selection tool. So you can find it easy in our website, or just type redexpert.com or .de, and it's completely free to use. I have shown some graphs in the presentation that had the Red Expert logo on them. That means you can find these graphs in Red Expert. On the left, you can have some you can use some useful designing tools. And in the right, you can find more product modules, like more focus on the product and for the component selection. For example, here you can find the MLCC module, and here you can find the electrolytic and polymer capacitor module, which we discussed before. So you can also click here and find more product modules. For example, other modules I manage as in the capacitor and resistor divisions like supercapacitors or safety capacitors and resistors. So I will show you one example. I have opened the MLCC module and I have filtered for 1 microfarad. Here you can see the filter is filtered from 1 microfarad and 50 volt. So you can filter for that in the columns. And then, well, you don't need to register to use it, but if you register to RedExpert and log in, you can use this functionality like moving these sliders. So if you move these sliders here, in this case, I moved the ESR and C impedance curves. In the sliders, I moved to 150 kilohertz, and I got the values of impedance and ESR in the table. So I don't have to look at the graph to see the values. So I also moved the slider in the DC bias curve to 24 volt. For example, if my application have 24 volt, and I can see the exact capacitance values taking into account the DC bias effect. Of course, as I showed you before, the orange part is the largest, and it will be fine actually at 24 volt, but the smaller parts will have a significant capacitance drop. That may be an issue. So with that, we reach the end of the presentation. And before we go to the questions, I want to remind you that you can write me or anytime directly to the email address you can see in the screen, and also for questions regarding resistors or other kind of capacitors, and also suggestions about webinars or anything else. If you think this course was interesting, we can also offer in-house, especially if this course was interesting for your colleagues, we can offer in-house seminars to have a closer discussion with you. Yeah, just contact us or ask your local sales representative, and we will be happy to arrange it if it's possible. So I hope you learned something, and yeah, I hope you had many questions. So yeah, I will try to answer the questions that you submitted.
Thank you very much, Jon, for presenting. We do have a couple questions that have been rolling on in here. Again, if you have any questions, simply tap the question mark, and then you can ask them in the questions box. Our first question here, what happens to electrolytic capacitors under DC voltage? And also, do we also have DC bias?
Yeah, so there is no DC bias effect on electrolytic capacitors. So under DC voltage, they only get better, as I show you with the self-healing property, and there is no capacitance drop. This is only happening to some ceramic capacitors.
Okay, thank you for that. Our next question here, what do we have to look at with film capacitors?
Yeah, I didn't talk anything. I didn't say anything about film capacitors. But yeah, film capacitors, they perform quite ideally, like ideal capacitors, more than the others, with, of course, with some series inductance and series resistance, but they don't have these special properties like I discussed. The only issue is that is some dependency with temperature and humidity. But 1 month ago or 2 months ago, I did a webinar on that topic, so you can maybe find it in YouTube or DigiKey.
Absolutely. We can include that in the follow-up email as well for people to replay. It's all about our film capacitor selection there. And another question that has come in, and it looks like it might be one of the final questions here. How does capacitance change with frequency for NPO COG capacitors?
That's a great question. So if you look back to the measurement I showed you with MLCC, the frequency was actually very stable the capacitance was very stable with frequency. So all ceramic capacitors actually don't have a dependency. So the capacitance is constant up to the resonance point when it goes up, but this is only very close to that resonance point. And there is no difference between class 2 or class 1 like MP0 or so. Nothing happened to capacitance. It stays constant up to the resonance point.
Okay, thank you very much, Jon, for presenting today's Würth Elektronik webinar partnered with DigiKey Electronics.
Thank you, Amelia.
And thank you, everybody, for joining us for today's presentation. As a reminder, you're going to want to not miss out on our next webinar. It's coming up August 16th. It's Transformers. What characteristics are important to you? Register online at www.we-online.com/webinars. And don't forget to listen to the new Würth Elektronik What's Up radio podcast, where we are turning our application notes, press releases, webinars, and so much more onto an audio format. You can download it on iTunes, Google Podcasts, Spotify, any major podcast streaming network. That's Würth Elektronik What's Up podcast. I'm Amelia Thompson. Thank you for joining us today, and I hope to see you soon.